Hello, everyone. This is Billy Younger. I'm your astronomy instructor for ASC 111. This was the Monday makeup day for the Zoom meeting that I missed on Thursday, I believe it was. Anyways, no students came. Of course, no one's required to, so it's not like anything wrong happened or anything, but I just wanted to maybe take this opportunity to go ahead and video a little bit of some of the typical questions students have in hopes that it might help you. The major things that we do that are even remotely mathematical are the things that scare students the most. So I thought I'd go over a couple of those things. For instance, Kepler's third law. Some students have difficulties using their calculator to actually calculate Kepler's third law. In other words, if I give you the astronomical units from, say, the sun to a planet or something orbiting our sun, then you should be able to tell me the period in years, and that's done by solving Kepler's third law. Also, if I give you the period in years of an object orbiting our sun, then you should be able to use Kepler's third law to find the semi-major axis of that orbit, and that's actually measured in astronomical units. So I thought I'd do something like that. So let's start off. I'm going to go ahead and turn on my document cam. So on my document cam, I'm going to say, imagine we found an object whose semi-major axis, and I'm going to use A for the semi-major axis. I found their semi-major axis A was in fact 10,000 astronomical units. And Kepler's third law is A in astronomical units cubed is equal to the period, which I'm going to call T in years squared. And if you forget that, remember the mnemonic that basically, or the mnemonic tool that basically, where do people celebrate New Year's in New York City? And everybody knows that location is Times Squared. So notice the time is squared. So that'll help you remember which one has the right exponent. So with that in mind, I can now use this to try to find out what the period is. And that's the question. We've discovered an object orbiting our sun. It has a semi-major axis of 10,000 astronomical units. I would like to use that information to find the period of the orbit of that object. Well, according to Kepler's third law, if I have A, which I have, I need to cube it, and then that will be equal to T squared. And then, of course, I do the opposite of squaring, which is taking the square root, and that would give me the actual T. So I'm going to say A cubed is equal to, and this is how you put it in your calculator. You type 10,000 in your calculator. And again, there's a lot of better buttons to use in this one, especially if you know your calculator inside and out. But I'm just using one particular button. And the button I'm going to use will either look like this. It's a caret key, or it might look like this, x to the y, or it might look like this, y to the x. Either one of those three that you have, and your calculator should have one of those three. You're going to click that, and then you're going to hit the exponent, which should be 3. Okay. When you do that, your calculator may or may not spit something out. So I'll put this equals mark with a question mark over top of it, because some calculators will immediately spit the answer out, and others will require you to hit equals. Of course, when I do this, I get 1 followed by 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hopefully your calculator will call that 1 times 10 to the 12th, or it might even have a thing where it'll just say 1 and then it'll have up here 1, 2, something weird like that. That is okay. That's just a different way of notating it. Some will have 1E12 or 1 capital E12. If you're using, for instance, a spreadsheet, it will have one of these in there. All of those are the same thing. But I happen to know from Kepler's third law that A cubed, which is what this is equal to, is equal to T squared. So now I can say, take that 1 with 12 zeros. Now, if you keep it on your computer, on your calculator screen, you don't have to type it in again. but I'm acting like you did just because maybe you screwed up. Now that's equal to t squared, and the opposite of squaring, which is an exponent of 2, is raising it to an exponent of 1/2. I've already mentioned that that's the square root. So if you know your square root button on your calculator, you can use that. It's just fine. The other part, when we do another problem where I'm solving for a instead of t, that'll become more problematic because plenty of students know their square root key, but they don't know their cube root key. So what I want to do is now use that same button that I told you before. It's either going to be this one, or this one. I'm just going to write this one this time. And this time I'm going to raise it to the 1/2 power because that's really the exponent that is equivalent to a square root. And we know that the 1/2 power is a decimal, is just 0.5. Again, you may or may not have to hit equals. And when you do that, you ultimately get 1, 0, 0, 0, 0, 0, 0. And by the way, on my multiple choice tests, this 1 million would be followed by astronomical units, say for answer B, and then answer C would be 1 million years. So you got to pay attention to the units as well. So the ultimate answer is T is equal to 1 million years. So you got to keep your wits about you in doing that. Now, I did this one specifically because I knew since I was given A, if I make A a perfect square, which 10,000 is, it's 100 times 100, then the math would work out super easy. Similarly, if I gave you a T that was already a cube, the math would be really simple. So that's another nice way to do it. So I didn't have to actually use the time to do my calculators, but by all means, you should be doing this with your calculator. Here's another example. Again, we're going to use Kepler's third law. I could just say, hey, I found a planet whose orbital period is 1 million years. What's the actual semi-major axis for that? And that would be fine. But I'm going to branch out a little bit and show you something a little simpler. Let's say that I found a planet whose whose orbital period in years is actually equal. I'm going to use the perfect cube again. I'm going to use it being 8 years. Okay, if that's the case, I would like to know A in astronomical units. What the heck is that? Okay, so again, I'm going to use Kepler's third law, which says A in AU cubed is equal to T in years squared. And according to Kepler's third law, when I have the period, I'm supposed to square it. So I'm going to take 8, type that into my calculator, again, hit my special button, which is either this, or this. I'm just going to write this one down. I will then, since I have T, I'm going to put an exponent of 2 on it. And again, I may or may not have to hit equals. Okay, well, that's just squaring. Again, if you know how to do your square, you don't have to do this new button, but I'm just showing you with one new button how you can use Kepler's third law. So now I've got 8 to the 2 power. That turns out to be 64, which, by the way, 8 was 2 to the third. That's how I know it's a perfect cube, because 2 times 2 is 4, times 2 again is 8. So when I square this, becomes 2 times 3 power, so this is 2 to the 6th. That's going to help me do my math in a few minutes when I go to solve the other part, so I don't have to use my calculator. I don't need you guys to do this math without the calculator. I'm just letting you, peek behind the wall and see what the Oz is doing. Specifically, I'm, doing some math behind it. So now I want to take that 64. Again, you just leave it on your calculator. You don't have to retype it, but if you accidentally screwed up and did that, you would need to. What you know is that 64, which is actually equal to T squared, is also equal to A cubed. And that's T squared, which also equals A cubed. So I need to do the opposite of cubing, which you probably know is cube rooting. It turns out that a cube root is the same thing as raising something to the 1/3 power. Notice it's the reciprocal of the 3. 1 over 3 is the reciprocal of 3. So I'm going to raise it to the 1/3 power, again, using my ultimately powerful super button, the caret or the x to the y or the y to the x. And of course, here's a little bit odd part, but hopefully most students recall that 1/3 as a decimal is 0.33333. As many of those as you can put in, say at least 5, and you'll be pretty good. But as many of those you put in, the more accurately you'll do it. If you actually did parentheses, say, left parenthesis, and then you did 1 divided by 3, and then right parenthesis. That would be as accurate as you could possibly get. But again, you don't necessarily have to do that. If you do like 5 or more 3s, you'll be fine. But again, you may or may not have to hit equals. And of course, this is the 1/3 root of 2 to the 6th. So I know that's going to become basically 2 to the 2nd, which is 4. Again, I might have an answer A that is 4 astronomical units and an answer B that is 4 years. You've got to know that you started with years, so you should be solving for astronomical units. So the actual answer is A equals 4 astronomical units. So that's the way you do Kepler's third law, again, using just that one special button on your calculator, which on my calculator is that one. Okay, this is your squared button. If you'd rather use that to, if I give you the period, you need to square it, you can hit this right after putting in the period. If you need the square root, you can hit control, that'll shift it to these blue things over top, and you hit that, that would be the square root. This is actually the cube root, and you can see it starts getting complicated. That's why I just showed you this one button. That's all you need. So hopefully that'll help you with your Kepler's third law. The other thing you need to know about using or doing some of these equations is what I call the wave equation. And this is a very, very simple version of the wave equation. It turns out that the velocity, or that a wave travels a distance. So here's a typical picture of a wave. This is a sine wave, for instance. This distance from here to here is lambda. That's one wavelength. It's the Greek letter, lowercase lambda. It looks like that. Okay. And the time it takes for that wave, or for that wave to travel one wavelength, is called the period, and that's given the symbol t, not like that. And it really is the time required for, if you're standing on a pier, let's say the Avon Pier near Hatteras, and you see the crest of a wave, or let's say you see the midline of a wave go directly under you, you start your timer, and then the crest goes directly under you, and then the midline again, and then the trough goes directly under you, and then you're back to the midline again, and you stop your timer. That would be the period of the wave. And it's measured like in seconds or years or minutes or whatever, usually in seconds. And there's this neat happenstance that if you find the period of a wave is 4 seconds, then you might want to guess, well, how many waves go by you every second? This is the period of the wave, which I just said, say, 4 seconds. And this is the wavelength of the wave, which might be, say, 20 meters, something like that. This is the wavelength. This is a period. I just asked you a neat new question. I said, well, if the period of the wave is 4 seconds, how long would it take a single wave to go by? That's something different. So that's frequency. That is the number of waves that pass by you every second. That's what frequency is. And if it takes one wave 4 seconds to pass you by, I think you all can figure out how many waves will pass you in a single second. And give you a little pause here to think about it. So it turns out if a period of a wave is 4 seconds, then 1/4 of a wave will go by you in a single second. So you can imagine it this way. Maybe this part of the wave is where you started the timer. You went 1/4 right here. You went another fourth right here. You went 3/4 right here, and then 4/4 there. That's it. So we have this neat expression that says that frequency is 1 over the period, and that period is 1 over the frequency. That's kind of wonderful. But we had already found out that velocity of a wave, v, is the distance traveled, which I said it travels one wavelength, divided by the time taken, just like your speedometer says miles per hour. Miles is a unit of distance, per means divide, and hour is a unit of time. Well, I know that it travels a distance of one wavelength in one period. Well, that's the same thing as the wavelength times 1 over the period. Well, 1 over the period is equal to the frequency, so I'll say that's the wavelength times the frequency. That's our wave equation. So velocity equals frequency times wavelength is another equation we use, and that requires some algebra. For instance, if I ask you to solve for wavelength, You want to solve for that, you're going to divide both sides by f, and that gets complicated. And I don't want you to do algebra. I don't care if you do algebra or not. I just don't want to require it. So whenever you have an equation that has one thing on one side of the equals all by itself, put that in the top of the circle. And then all the things that are inside here, you put them in the bottom of the circle next to each other. So that's a f, that's a lambda. So if I ever want to solve for the wavelength lambda, I cover it up. It looks like the v is on top of the f, so you do v divided by f, and that would give you the wavelength. If you want to solve for the frequency, you cover up the frequency. That looks like the velocity is being divided by the wavelength, and that's how you get the frequency. Finally, if you wanted to solve for the velocity, you cover it up, and that looks like the frequency and the wavelength are next to each other. And sure enough, that's what you do. You multiply them. So that's the wave equation. That's how you work with that. Now, you've probably seen in some of your practice tests some of the problems we do with that wave equation. And I wanted to make sure you understood how we were doing those. And we were specifically talking about radio stations. So one of the typical problems I asked in my practice tests, my midterms, my final exams, all that good stuff, is what is the wavelength of, let's say, AM 850? So I want to know the wavelength of AM 850. Well, you might think, well, crap, I know an equation that gives me wavelength, and that's that nice circle that Mr. Younger just showed me, which is V, F, and lambda. And by the way, this lambda should be measured in meters. This frequency should be measured in hertz, and this velocity should be measured in meters per second. Okay. So if I ask you that, you might think, well, I want to use that, but seemingly have a number. I have an 850, but I don't know if that's one of these numbers or not. And that's all they gave me. Well, the big deal is you've got to realize that radios send out radio waves, or radio stations send out radio waves, and those radio waves are part of the electromagnetic spectrum. And the electromagnetic spectrum can be remembered by great excess. Notice how I spelled excess with an X, which is wrong, right? Great excess undermines various industries, Marxism, rules. Now, that's just me being funny because I'm a big, or was a big Rush Limbaugh fan. Been listening to his program, actually watching on TV since 1988, and listened to it rather faithfully for decades now. But he always made jokes that us teachers were all communists, so I sort of pretend like I'm going on with that idea. I'm certainly not a communist, but this clearly Karl Marxian type statement is consistent with that. And it's great excess undermines various industries' Marxism rules, the great being related to Bill Bixby and the Incredible Hulk. This being related to what happens when you go to a hospital after breaking a limb. This one allows you to get a pretty tan or even skin cancer. I think y'all know what this V one is. This one keeps your French fries warm at the Shake and Shake, which recently went out of business, much to my chagrin. This one warms up your Hot Pockets. And then this is radio waves. So the reason why you memorize that is this is the electromagnetic spectrum. All of these types of waves are electric fields oscillating in one plane and magnetic fields oscillating in a perpendicular plane going in yet a third direction. Okay, so all of these things are electromagnetic waves and are found with Maxwell's equation. And because of that, they all travel at the same speed. V equals C, which is about 3.00 times 10 to the 8th meters per second. So because I know radio stations send out radio waves, I know this wave is a radio wave, and therefore I know its speed. So I've got V already. Then it's just a matter of realizing, what does AM 850 mean? And my daughter, when she was about 9, asked me, my oldest daughter asked me, Daddy, do those numbers mean anything, or are they just some stuff the car makers made up? Well, that was a really astute question, and it actually is right. It does mean something. In fact, AM 850 means that the frequency is equal to 850 kilohertz. So in fact, you should type this in if you need to use it in your calculator as 850. And your calculator will have an EXP button, either an EXP button, or it'll have a times 10 to the X button, or something like that. So you'll either need to use, like I said, the EXP. I didn't write that very clearly, so I'm going to write it again, EXP button. And what that means is if I type in 850 EXP, then it's going to basically pretend what you just wrote down was times 10, and then the number you put next will go in that exponent up there. So 850 times 10 to the third is the frequency in hertz that this radio station is. Kilo means 1,000. So this is really 850,000, which you actually, if you wrote it in actual scientific notation, it would be 8.50 times 10 to the fifth. But your calculator deals with it whether it's scientific notation or just this 850 times 10 to the third. So you can just use that. So that's what you need to remember about AM is kilohertz. So you're going to have to put whatever station someone gives you in AM, you're going to have to hit a EXP3 after it to get the actual number. So if I want to now calculate the wavelength, I now know the frequency and the velocity. And according to this, all I got to do is derive the velocity by the frequency. So I'm going to say lambda AM 850 is equal to, and here's how I put it in my calculator. I got to do the velocity divided by the frequency. So I'm going to type 3 EXP 8, and that's 300 million, by the way. That's 300,000,000 meters per second. Now that's not exactly right. In fact, it's 299,458,792 or something like that. But just roughly, it's 300 million meters per second. Then I'll hit the division button. Then I'll hit 850 EXP 3, and then again, I may or may not have to hit equal, so I'll put that down. And when I do this calculation, I get 352.94. Now, the thing is here, just like before, I might have answer C is 352 or 353 hertz, and answer D might be 353 meters. Okay, so you got to keep your wits about you and realize, wait a second, they asked for the wavelength and they gave me, sort of by hiding it, they gave me the frequency and the speed. So this actually has to be in meters. So we say the wavelength of AM 850 is 352.94 meters, or you just find the closest one, of course. I would never do 352.9 versus 352.90. I would never do anything like that. But that's how you find the wavelength. And you can see this is actually large. Remember, a meter's about 39 inches, so it's bigger than a yard. So we're talking like 5 football fields, basically, is the length of this wave. So literally, another way we can think about waves is instead of going from midline to peak and so on and so forth, you could just go from peak to peak. That's also a wavelength. So you can imagine this wave from here to here being 4 or almost 5 football fields long. And despite that, 850,000 of them pass through you every second, and you start to get an appreciation for how big the velocity of light is. The speed of light is super, super fast. So that's that. But you also see from this, oh, I bet this side must be really long wavelength. And in fact, it is. This side must therefore be short wavelength. And that's true as well. There's other relationships, of course. For instance, we found since velocity is equal to frequency times wavelength, and for each of these waves, the velocity is the same. If, let's say, we're using units where the speed of light's 100, then this could be 10 and this could be 10 because 10 times 10 is 100. But if I change this, in other words, the frequency, which was 10, and the wavelength, which was 10, if I change this frequency to 5, the frequency went down by a factor of 2. In other words, I took 10 divided by 2 and got 5. Well, what happens to the wavelength? This product still has to be 100 because the velocity of light in these units is still 100. So in order for us to multiply 5 by something to get 100, we realize that's 20. So that frequency going down by a factor of 2 must have meant the wavelength went up by a factor of 2, because 10 times 2 is 20. So from that, we see that frequency and wavelength are what we call thumbs up, thumbs down. One goes up, the other goes down. So with that in mind, you can say, oh, well, this must be, since that's short wavelength, this must be high frequency, and this must be low frequency. And from Planck's famous equation, E equals HF, we now know that high frequency implies high energy too. So this side is high energy as well. So that helps us figure out all that stuff about the electromagnetic spectrum, even though I was really just showing you a wave equation, or how to use a wave equation to find a wavelength. So one more example that you need to know is, what about if I give you instead of an AM radio station, an FM radio station? So let's look at Bob FM, which is the radio station I generally listen to. So I'll say, what is the wavelength of FM 93.7? Okay, well, you might suspect that FM might be different than AM, and in fact it is. AM means amplitude modulated. So what they're doing is they're actually putting the sound signal in a thing that multiplies in front of the amplitude here. So the amplitudes go wee, 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 weird stuff like that. That's the AM. Whereas this one takes those frequencies, the number of waves per second, and multiplies that by the radio signal, the music basically, and that makes them look squishy next to each other, and sort of like a various parts of a slinky when you're stretching it out and someone's pushing pulses back and forth. So this is a frequency modulated, and it turns out the frequency modulation number is actually in megahertz. That's capital M hertz. So this means when I want to know that, if I say FM 93.7, you've got to understand that means 93.7 megahertz, and mega means million. So you should think of that on your calculator as 93.7 exp again, 6. So you're actually going to move this decimal 6 places to the right, just like you moved the decimal to the right of 850, because I gave you as AM 850. You'd move it 3 places to the right. So the same thing happens here. Again, our velocity circle, our velocity wave equation circle, gives us that lambda is found by dividing the velocity by the frequency. Radio waves in the FM are still radio waves, so they're still traveling at the speed of light. So I could say wavelength of FM 93.7 is in fact equal to the speed of light, which I'm going to say is approximately 3.00 exp 8, that's 300 million meters per second. Now I got to divide it by the frequency, and I'm going to call the frequency 93.7 exp 6. And again, your calculator may or may not require you to hit equals. So I'll put a question mark over top of that. And when I do this calculation, I get 3 e to the 8. My calculator, by the way, has a E button. So that's another button. It can have EXP, EE, or that 10 times 10 to the X. So I'll do 3 EE8 divided by 93.7 EE6, because it's megahertz. And with that, I get 3.2017. Again, you have to keep your wits about you. 3.2017 might be in seconds, might be in years, might be in meters, might be in arc seconds, all sorts of weird stuff. You've got to find the right unit, and the right unit, of course, is lambda AM, or excuse me, lambda FM 93.7 is actually equal to 3.202, whoa, 3.202 meters. And that's how you do that problem. I hope that clears that up for you a little bit. So that's how you do those problems. The only other problem I really see a lot of students having difficulty with, other than the moon phase problems, which really takes a whole big process to explain all that, but you guys can certainly check it out on my YouTube channel where I have that worked out, and I have actual examples worked out. But the other one really is this Bohr model of the atom and how you can predict what parts of the electromagnetic spectrum were each photon for each transition. So I could draw, for instance, a nucleus of an atom right here. There's a nucleus. And then the way it works is you have the Bohr model, which was wrong. It worked perfectly for hydrogen, but it was sort of wrong. But the part that it got right was that there's certain allowed orbits and nothing could be allowed in between. So there's a very distinct energy difference between one orbit and the next. And that energy difference from one orbit and the next is more or less a fingerprint for an atom. And it turns out the same thing is true for molecules. There's another fingerprint for molecules. And though we can't necessarily work out all the gory details, we can certainly measure them and understand them. So when we see certain wavelengths of light being emitted or absorbed in a spectra, we can say, oh, well, this element's here, and this element's here, and this is hydrogen, and this is helium, and this is titanium oxide, and this is carbon monoxide, so on and so forth. So this would be, for instance, the average radius or the most likely radius of the first orbit, and it would have an energy E1 because it's the innermost or the n equal 1 orbit of the electron. Then there's another one out here like this, and that would be, say, E2. And as they get further and further out, they get closer and closer together. So the next one might be E3. And of course, with that is a R2 and an R3, but I'm just caring about the E's right now. And then closer still might be an E4, like that. Then the big question is, what is the actual photons? Are they actually emitting photons in this transition? Are they absorbing photons? So some of the transitions you might think about could be arrows pointing up or arrows pointing down, and each one's very different. An arrow pointing down means an electron went from up high to down low, so it actually had a lot of energy and it fell down to a lower energy. Conservation of energy says that energy is not just destroyed. In fact, that energy will be made into a photon, and a photon will shoot out in a random direction the instant that electron falls down here. So it's being emitted, and therefore arrows that point downward are emission spectra. If the arrows were pointed up, they would be absorption spectra, because the energy has to be absorbed. The photon has to disappear. Its energy then goes into kicking an electron up higher. So that's one arrow. There could be another arrow here where it's going from E5 to E2. There could be another arrow here where it's going from E5 to E3. And then finally an arrow here, which is going from E5 to E4. Obviously, each of those are different lengths, and that's a relevant thing. You could even find another one which might be a little different, like I could go from E4 to E2 or something like that. The main thing is, what you realize is that the heights of these are directly related to the energy. So this one has this height, that's a certain amount of energy. This one has this height, that's another amount of energy, another amount, another amount, another amount. So what we say is the length of the arrow is directly related to the energy. So I'm going to call this little guy number 1. I'm going to call this little guy number 2 and number 3. And this one will be number 4. And let's say this is the diagram of some electron transitions that we know to have occurred in a particular atom coming from the spectra of a star. One of the questions I might ask you is this an emission spectra or is this an absorption spectra? And of course, you're seeing the arrows going down, you would say emission spectra. So the down arrows imply emission spectrum. So that's one type of question I could ask you. But I could also say the photons released are, let's say there's a red one. Let's say there's a microwave one, which that's the Greek symbol of micro, so I'm just going to use that instead of writing the word. Sorry about that if that's a pain in the butt. There will be an infrared one, and there will be a yellow one. So those are the 4 photons that represent these transitions. My question then could be, okay, well, what is the actual red photon? Is it transition 1? Is it transition 2? Is it transition 3? Is it transition 4? What about the microwave? I should write that, microwave and infrared. So this is the infrared, this is the microwave, this is yellow, this is red. So how do you answer this? Which question is which? Well, what you got to realize is this one is the highest energy because it's the longest arrow. This is the second highest. This is the third highest, and this is the lowest energy. Then you just recite your great excess undermines various industries' Marxism rules, and then you take the visible spectrum, and you probably remember the parts of the visible spectrum as Roy G. Biv, but in the way that we've ordered this is actually backwards to that. I think you can tell that because Biv ends in V for violet, so violet should be next to ultraviolet, and of course Roy G. Biv starts with R, and R should be next to red, or is red, which should be next to infrared. So it actually becomes Vib Gior, like that. Okay. So that's Vib Gior. Now what we do is we say, okay, let's go from the left-hand side, which we know is the highest energy. We just found that out earlier. It's also the highest frequency. It's also the shortest wavelength. And it's also the highest temperature, which probably makes good sense to you. Okay, so highest energy, highest frequency, highest temperature, and the shortest wavelength. So now we just put these things on here in the order that we come to them. So number 4 is the highest energy, so it must be close to this end. So is red closest to this end? Well, red's there. Let's go ahead and put an indicator. That's red. There's also a yellow. There's also a microwave, and there's an infrared. So those are our 4 photons. Obviously, the highest energy one is the yellow, so yellow is going to be 4. And of course, our next highest is the red, so red must be 3. And then the next highest is infrared, so infrared must be 2. And microwave should be the weakest or the lowest energy, and that should be 1. So I could ask you, what is transition 1? That's one question, and by working this out, you'd say that's microwave. I could ask you another question, which one is the yellow? And you'd say, oh, well, the yellow is transition 4. So you see, I got like 4 questions, 5 questions. I could just ask you to do all of them, or I could ask you each one individually. I could also ask you the question about whether it's absorption spectra and emission spectra. But the whole deal with figuring out which photon's which is the longest arrow represents the largest energy. In fact, 4 means E5 minus E1. And of course, you would set that equal to H times frequency according to Planck. And that would allow you to figure out what color it is, really. So if we were doing a more mathematical class, I would give you these energies and you'd subtract them and set them equal to HF divided by H, which is Planck's constant, and you get the frequency. Or you could just subtract them and see that the energy is such and such, and then you could say, well, this energy is in this part of the spectrum, so on and so forth. But again, I don't make you do these. Transition 3 would be E5 minus E2 equals HF52. This would be 5,1, so on and so forth. That's really what's going on, and that's why the energy difference is directly proportional to the length. So the longer the arrow, the bigger the energy. I think that's a pretty good indicator of the types of stuff that you guys, our astronomy students in general, tend to worry most about. So I wanted to make sure at least to give you a chance to see that for you specifically. Actually, I just thought of another thing I should probably do. So let me do this as well. One more thing. This will be Wien's law. This is Wien's law, W-E-I-N apostrophe S law. Now there's an equation for it, but it basically just says the temperature at the peak of that famous Planck curve is inversely related to the wavelength at the peak. In other words, if you made a plot of temperature versus wavelength, okay, well, according to the history of physics, we've basically known what this plot looks like. When you heat a iron rod up, like a horseshoe stake, say, you heat that iron rod up, and then you measure the spectra from it. What you see is a whole band of wavelengths of light coming from it. And when you make a plot of that as a function of, excuse me, I said T, as a function of energy, I apologize for that, as a function of energy, what you'll find is there's a very steep part of the curve going up, and then it comes over into a peak, and then it gradually falls off very, very slowly. And the area under that curve turns out to be the Stefan-Boltzmann law, which basically says that the luminosity is equal to some constant times 4 pi times another constant called the Stefan-Boltzmann constant times the square of the radius of the star times the temperature of the star to the 4th power. Okay, that comes from taking the area under this curve. This peak, however, if you take the quote unquote derivative and set it equal to 0, you get something called lambda peak. That's the lambda. It's not the highest wavelength that the thing puts out. As you can tell, there's a buttload of those and it seems to go on forever. It's actually the wavelength at which this peak occurs. And that peak, if you divide some number, and it's 2,900 micrometers per Kelvin, they have it in different units. Sometimes it's nanometers, so on and so forth. But basically, if you divide that number by lambda, you'll get the actual temperature of the star. And that is, in principle, a way of finding, for instance, the temperature of a human. That's not unlike the thing they now put against your forehead or aim at your forehead to check your temperature, for instance, for COVID or whatever. It actually is, in principle, making a plot like this for your body. Then it's finding the peak, and then it's using Wien's law to find out the temperature of you, and then it's making corrections for the fact that they've studied a lot of humans and they know that your core temperature is different from your face temperature by a certain amount, so it corrects for that. But basically, it's using Wien's law to figure out your temperature. Now, the other part about that's neat about Wien's law is where this peak is really matters, because if this peak happens to fall within Roy G. Biv, okay, so this might be, for instance, the red end of the spectrum, and this might be the violet end. Like this, okay, then clearly this star is going to be sort of greenish or yellowish. But what if instead our star looks like this? Okay, well, then the peak is out here, so we have to revert to the highest part of this curve that's in the visible spectrum. So this star, in fact, would appear red. Similarly, if we had, say, I'm going to use black this time, which you can't tell much difference between black and blue, but if I had this star, and generally this one would be much, much taller than this one. This one would be much, much smaller than this one, just because of temperature and the sizes and whatnot. This peak right here obviously is also outside of the visible spectrum, so you can't say its color is, ultraviolet. Instead, you would find the part of the curve that's in the visible spectrum, and that, of course, is on the blue end. So you'd call this star blue, even though it's sort of violet. We just, we pretty much call stars red and blue, and that's and maybe orangish, and that's about it. So this one's going to be called a blue star. So that's how Wien's law allows us to figure out the color of stars. if we're lucky enough to have it in the visible spectrum, then it'll be that color. And in our sun, for instance, if you actually calculate the wavelength, you'll see it's right around in green. But our eyes are not very good at detecting green light with their rods and cones. The cones being the ones that are responsible for color. They don't do green very well, so we end up seeing it as sort of an orangish star. Those of you who want to, you can get some astro points extra credit for writing an essay on why we don't see green stars. It probably only needs to be 500 words. You can turn that into me if you like, but that's good enough. I think I've done way more uh, than maybe you wanted, but I wanted to actually give you an opportunity to explain some of the things that we're doing, some of the more sciencey things. Now that we've gotten out of the more sciencey chapters, we're just applying that science to understand how stars behave, or how we can look at a star and understand what's going on inside of it. I think this all helps that. So I hope you all have a good day. I will be having my recurring office hour type help sessions type Q&A session for AST 111 that occurs on Wednesdays at 1 p.m. So maybe y'all can make it to that one since you didn't make it to this one. Have a good day. Bye-bye.